On problem number 2, but we got 4 to do. And 4 is asking for the Lewis structure of the hydroxide polyatomic ion. Okay, and remember that that minus there actually means -1 in this case. So let's go ahead and do wants. Oxygen wants 8, and hydrogen wants 2. It's one of those exceptions. Minus have. Oxygen has 6, that S2P4 we talked about at the very beginning of this practice final. And hydrogen has 1, and then the whole molecule actually has 1 extra, so we put that there. And that is for that 1 extra, okay? So then here we have 10 minus 8 is 2 divided by 2 because they're locked in covalent bonds, and that's 1 bond. So we're gonna put it in brackets, and there's your 1 bond. Hydrogen has what it needs, but oxygen needs the rest. So this entire thing is an ion, but it's a polyatomic ion. So it's kind of interesting. We have ionic character here, and then there's those 2 electrons locked in this 1 covalent bond right there. Okay. So that is a linear molecule, and if we can go on here to 5 and talk about what would happen if that molecule were mixed with water. So we know that water is your standard polar bent. You know, and I'm gonna go ahead and keep these partial charges done in red. That's so ghetto, come on, Ramsey. So oxygen pulls harder. So it's kind of negative. It's not fully negative because those electrons are still being shared. And this minus is gonna be attracted in a very strong fashion to that positive right there, and that is an ion. So we know that that intermolecular force is called an ion to a dipole intermolecular force, and it's a different intermolecular force than you would see with dipole-dipole. It's stronger, and it tends to be what you see when you have an ionic compound like salt dissolved in water. Okay, so we're down here. And actually, here we go. We're moving on to problem number 3. So, in problem number 3, we have your typical airbag problem. So, first thing they want us to do is balance this reaction. So we have NaN3, that's the solid sodium azide that's contained in the airbag, along with iron oxide, which is the same component as rust. That produces sodium oxide, iron metal, and our nitrogen gas, which I'm gonna draw the Lewis structure to up here. It's very ideal, it's very small, and it's very stable because of that triple bond. And we're gonna go ahead and balance this reaction, and when we do it, we need to be putting a 6 right there, which allows us to put a 6 right there. No, we don't put a 6 there, I'm sorry. What am I doing? Come on, Rams. So, Na, we have 3, we have 2. 3 and 2, then we have a 2, so 2. And we have a 3 and a 1. So what I'm gonna do is put a 3 there, and I'm gonna balance the oxygens, which makes that a 6 there, okay? We got a 2 there, I'm gonna go ahead and put a 2 there. But now, look at what we have. We have 18 N's, so I'm gonna put a 9 there. And we are balanced, okay? So now the airbag, it contains 17 grams of sodium azide and 250 grams of iron oxide. And they wanna know, in this case, what volume of this is produced. So any time, guys, that you have numbers with a reaction, you're gonna be doing an ice table, because the ice table essentially is how we use numbers in a chemical reaction. There's no other thing you can do. That's it. We got to use the recipe to solve the problem. So there's 17 grams of NaN3 and 250 grams of Fe2O3. Well, we speak the language of moles. That's what we speak. So NaN3, or NaN3, is 65. Okay, it says that the molar mass of NaN3 is 65, and we have 17 grams of it, so we're gonna take that 17 and we're gonna divide that, 17, we're gonna divide that by 65, and we got 0.26 moles here. And then it went on to say that we have 250 grams of Fe2O3. So I'm just going to be super ghetto here and say, what is the molar mass of Fe2O3? And we see that that's 159.69, 159.7 divided by 250 is 0.6388. I'm just going to go to 0.64. Okay, so when I look at this, I know that I have 0, 0, 0. And I look at this, and immediately I know that I need 6 times as much NaN3, but I don't have 6 times as much. I actually have 3 times as less about. So I know that ultimately this is going to be my limiting reactant, but this would be minus 6x, this would be minus x, this would be plus 3x, this would be plus 2x, and this would be plus 9x, okay? And I'm gonna go through here and solve this problem. So to solve for x, 0.26 divided by 6. Okay, I know that x is 0.043, and then I'm just gonna go ahead and put x right up in there, times 9. So I have right here what I'm looking for is 0.39 moles of N2, okay? But they're not asking for moles of N2, they're asking for a volume of N2. So V equals nRT, and this is actually the answer to B. nRT over P. So I'm gonna solve that over here. We know that we have 0.39, 0.0821. The temperature that they gave us was 21 to 273, 273, 293, 294, divided by P, 0.9. So 0.39 times 0.0821 times 294 equals that divided by 0.9 equals 10 liters. And in the problem, there are 3 significant figures, so 10.5, and that makes sense about the size of a car airbag. That nitrogen is a really, really good molecule to use because it's ideal and it's going to want to expand. That's really what gases want to do. So, oops, I lost you over here. I'm looking at the quiz on the computer. Determine the mass in grams of excess reactant that remains. Oh, I erased that. Ugh. But in that case, you would just take your Fe2O3 that was remaining, and you would convert that to grams. So I forget how many moles were there, but whatever you got from the ice table there, you would take the molar mass of iron, which we know is, it's 159.7 grams per every 1 mole, and you would have X grams per every however many moles you got from the problem. So sincere apologies about that, but something tells me that you guys are pros at doing that kind of conversion. So let me look back at the problem here. 2, do you predict the final pressure inside the bag? So let's look at C. Here we have this bag, and we have the nitrogen gas that's expanding. Now remember what this nitrogen gas really looks like is this, and it's small and it's nonpolar. But they're saying, what if you replaced it with SO2? Okay, clearly explain, would the pressure be higher, lower than N2? So if you do the Lewis structure for SO2, you end up with 3 bonds and you get a bent molecule, okay? And this bent molecule is actually polar. So these SO2 molecules, let's just draw 2 in here. There's going to be this intermolecular dipole force here, so there's going to be less expansion. These are just going to fly apart from each other, and these are going to be kind of stuck to each other. So there's going to be less force on the walls of these containers. So the pressure is lower. SO2 is polar, and therefore this means therefore, I don't know if you know that, the IMFs acting between the SO2s are stronger, and they expand less. Okay. So that is C, and let's finally move on here to the final problem, problem number 4. Okay, and this is a hydrate problem. So to remind ourselves, it's a hydrate of copper to sulfate. So copper to sulfate hydrate. So that 2 means that the charge of that is +2, and this ends in 8. So you go on the periodic table, and sulfate is the polyatomic chart, and SO4 is 2-. And we end up with CuSO4, and it's a hydrate, so we have some value there. We'll call it NH2O, and really what we're trying to do is find N. So this is a grams to moles divided by the smallest problem. So remember that when you heat these kinds of substances, if we were to heat this, the water is going to leave, okay, in the form of H2O vapor, and we're going to be left inside the container with simply just CuSO4. So we look at the data and we see that the initial mass of the sample and the container before heating was 37.6102. And then we heat it to constant mass and we see that the mass stabilizes, and it eventually goes down and stabilizes at 36.9600. We see that the mass goes up a little bit. So maybe it oxidized, so I'm gonna stick with that 39.66. Well, this drop in mass is due to the water that left. So let's go ahead and subtract those two. If we subtract 37.6102 minus 36.9600, we get 0.6502 grams of H2O. Okay, now let's go ahead and get the grams of CuSO4, and then we just do grams to moles divided by the smallest. Well, if this left, this was left behind. So the mass of the empty container, just the container itself, when we look at it, was that first piece of data, 35.8490, okay, and the mass of the whole container after heating was this number here, 36.9600. So this contains the substance, and that's without it. So let's go ahead and subtract those two. So 36.900 minus 35.8490 equals 1.051 grams of copper sulfate that are left behind. So now what I'm going to have to do is convert both of those values to moles. So the molar mass of copper sulfate is copper sulfate molar mass. What are you, babe? You are 159.6. So I have 1.051 divided by 159.6. And that equals to 0.0066 moles. And then I got my 0.650 divided by 18. That's 0.036 moles. So that's essentially the formula. Like, this number is essentially that value for N. But we want to divide both by the smallest. So we know that 0.006 is the smallest. And then we take that 0.036 and we divide that by 0.006, and I get 6. So that's that value right there. So the answer in this case is 1 CuSO4, 6 H2Os, and that's the value in the formula for the hydrate in that case. Now let's go on and look here. see if I have, if there's any other problem that was associated with that. So I'm gonna scroll all the way down. Okay, that was your answer to A. Okay, there it is. Now I'm gonna erase all this garbage down here, and we're gonna answer B. One sec, Justin. B. Okay, explain why one can conclude the hydrate was heated sufficient number of times. Because it was heated to a constant mass. Okay, which means in that circumstance, with continuous heating, no water was left because it was fully dried. In C, when performing the experiment a second time, some of the sample splattered out during heating. How would this air impact the calculated formula of the hydrate? So it would increase the H2O value. You're getting H2O by subtracting the initial and the final value before and after heating. So the scale would, not that it's alive, but the scale would think that the mass splattered out was H2O. Doesn't know any better. It's just giving us numbers, and we're using those numbers to calculate the H2O. Therefore, increasing or elevating the H2O mass and eventually mole value. So we'd get a value there greater than that.